Hello pre-calculus students. Today we look at analysis of polar graphs and polar equations, and the first thing that we're going to investigate here today is polar equation symmetry. So, and we're going to start with these rules for symmetry, and there's a way that these rules can be proved. And if you want to see the proof, you watch one of the other videos. But in this video, we're going to take these given rules for the proofs of symmetry and apply them to some situations. Okay, so the first symmetry that we're going to consider is symmetry over the x-axis. And so that would be an example of a graph like this. Let's say you had a graph of a circle like this, and you can see that the symmetry over the x-axis means that the top half of the graph and the bottom half of the graph are identical. So it's like the x-axis serves as a mirror. And the graph itself tells us and gives us a really good idea about symmetry, but it's not a proof of symmetry. And the only way we can prove that a graph is symmetrical or has some sort of symmetry is by using one of these rules. So if you want to prove that something has symmetry over the x-axis, you're going to take r theta and replace it with r negative theta, and then do some sort of work with the identities to show that the equations are identical. Or you can also replace r with negative r, theta with pi minus theta, and then show that the equations are equivalent. Next, we move on to a symmetry over the y-axis. And so this would be an example of that. If I had a circle, this, underneath the x-axis, you can see that if you use the y-axis as a mirror or the line of symmetry, the left side and the right side would be identical. So this is symmetry over the y-axis. And to prove that this is true, we take r theta, replace it with negative r, negative theta, and do some work on it and show that the equations are going to be identical. Or we can keep r the same, replace theta with pi minus theta, and then show that the equations are eventually going to be the same. Finally, we have symmetry about the origin, and about the origin really means symmetry with 180-degree rotation. So, in other words, if you take the picture and you spin it 180 degrees, you still have the same picture. So this would be one of the this would be an example of something that has symmetry about the origin. In other words, if you take this graph right here and spin it 180 degrees, take this board here and literally spin it 180 degrees, you would get the same picture as you did before. So this is with it rotated, spin it 180 degrees, and you get the same picture again. Okay, so this is symmetry about the origin, and the way we can prove that is by replacing r with negative r and proving that the equations are identical. Or we can also replace theta with theta plus pi and show that the equations are identical. Okay, so these are the rules for proving the different types of symmetry in a polar graph. And I'm going to pause this for a minute, and we're going to do an example on how to apply and use these rules. So we have a problem here that says determine if the equation r equals 1 minus 3 sine of theta has any symmetry. And when it comes to any problems that involve symmetry, the first thing that we're going to do is check by using a graph. Okay, so the graph itself isn't really a proof, but it certainly is helpful if we can graph it. So let me clear things out here, make sure that I am in polar mode. I'm going to graph this in radians. Go into my y equals, and I'll graph 1 minus 3 sine of theta. My window is going to go between 0 and 2 pi. Oops. And we'll increment this in half a radian at a time. The X min in this case, we'll just go with the standard 10 by 10 window. And we can hit graph. And you can see there that the graph is very tiny. It's kind of jagged. So what I'm going to do is decrease the theta step a little bit to 0.1, and hopefully that'll give me a more smooth graph. So with polar graphs, the bigger the theta step, the faster it's going to draw, but it's going to be less accurate. The smaller theta step, it's going to be more accurate but take a very long time. So you kind of want to balance those two. Okay? And I'm going to change my X and Y window to 5 and -5, just so I get a better picture of this. Now you can see that it's drawing in there, and by looking at this graph on its own, I can tell that it's got Y symmetry, or symmetry over the y-axis. Okay, but just by looking at the graph. But keep in mind that this is not really a proof. So it has symmetry over the y-axis. But now we actually have to prove that the symmetry is there. So the second step is to prove symmetry using one of the rules. So let me bring this back here, and you can see here that it's the second rule that I have here that's in question is symmetry over the y-axis. I can replace r with -r and theta with -theta. Okay, so I'll write it over here. So we're going to try with our proof, okay, and we're going to try with -r and -theta. So we start with our original equation. Okay. R equals 1 minus 3 sine of theta, and we are going to replace r with -r. Okay, and that was really the 0th step. This is the first step here. We are going to, let me get a better marker here. We're going to replace r with -r and theta with -theta, okay, and attempt this proof. And my goal again is to get this statement -r equals 1 minus 3 sine -theta to somehow equal the original. So I want to show that this line right here is somehow really equivalent to this equation up here. So the first thing I'm going to do is multiply both sides by -1. So that gives me positive r, -1 plus 3 sine of -theta. So I'll put my reason on this right side here. Multiply by -1. Okay, and you can see that by doing that I get an r. So the equation that I have now closely resembles the original. And in my next step, I want to somehow get rid of this -theta. I want it to become positive theta again. And the only way that I can really do this is using some sort of trigonometric identity. So I can't really multiply this. You have to resist the urge to just to magically multiply this by -1 because it's an angle inside of a trig ratio. Okay, so all I can do here is change this into negative sine of positive theta. And my reason for that is an odd identity. And this goes back a little bit to the previous section, the previous chapter that talks about trig identities. Okay, and I'll put in quotes here that sine of -theta is equal to negative sine of positive theta. Okay, this is an odd identity that we learned previously, so we can apply it here. And we'll just simplify the equation a little bit. -1 minus 3 sine theta. Okay, and I'm getting very close to what I want, but it's still not quite there. And instead of having a positive 1 here, I have a -1, so that doesn't really give me what I want. And I can probably do some more stuff here that's going to make things a lot more complicated. But at this point, it might just be better to retry with the other possibility. So I'm going to remind you of the two rules here. We have this rule up here that we tried already and we didn't succeed. And so now we're going to try this rule. Okay, so we're going to try one more time with a different rule. So just copy this down. I'm going to erase it and we're going to try it again with the other rule. Okay, so we tried it one way and it didn't work, so we're going to try again with r pi minus theta. So my first step, I'm just going to copy down the original. And then I'm going to change, r is still going to be the same, but I'm going to change theta to pi minus theta. Okay, and now my goal is to somehow to undo what's in here and show that it's really equivalent to sine of theta. And whenever I have a statement that has a difference of an angle, I got to use the sine of a difference or cosine of a difference. So make a note here. And sine of pi minus theta is really the same as sine of pi cosine of theta minus cosine of pi times sine of theta. And my reason is the sine of difference. And now this is going to allow me just to simplify what's inside the brackets here. Sine of pi is 0, so this entire term here is going to give me 0. Minus cosine of pi on the unit circle is -1, and I still have sine of theta. So I'll make a note here that sine of pi equals 0, cosine of pi equals -1. Okay, this is my reason that I'm writing over here. Okay. And so now I can simplify this further. I get r equals 1 minus, and this is just going to be -3 minus 3, and this negative and negative is going to cancel. It's giving me a positive, so it's going to be sine of theta. Okay, and you can see that this expression down here and this expression up here are identical. So this is same as the original equation. So I'm done. And with this proof, I've shown algebraically that the function r equals 1 minus 3 sine theta is in fact symmetric, and in fact symmetric over the y-axis.